Hello, welcome back. So in the previous video, we were aiming towards something like this, to making a binary clock example in which we can have all of our little clocks ticking round, showing how in counting in binary, it can be thought of as just individual clocks, with each clock having half the frequency of the previous clock, all spinning round and just counting like a regular clock would. We got to the point where we implemented a single clock on our grid, and the aim of this video now is to implement all the required clocks that we need. So the first thing I'm going to do is I'm going to move the clock that we just created to a different location. So rather than being on the top row, I'm going to move it on the bottom row. So look at that. See, now it's on the bottom row. Now we need to come back to this here. So what do we call it? Class T mod num. So it's a modulated time number. Let's go ahead and give it basically the same initialization here as the clock. So frequency, axis, base and scale. Give a default base of 2, default scale of 1. And then we can go ahead, again, copy some more code. It's always good to copy code. And because we're actually using a lot of the same code for these two classes, what we could have done is created one more class above those two. And then these two classes could have inherited these methods from those classes. And then we could have overridden as needed, but actually the overrides would have made it so the total amount of lines of code would have been longer. So it's not actually as good. And then in our initialize function, we can have the same thing. We do want time, we want to get rid of the axes. Don't necessarily need to do the display limits, but we'll do that anyway. So there we are. Successfully copied that over. And then we need to add some text. So we need a text object that just sits in the middle and then simply counts. So that's self.text. So create an object within the class itself called text. And then to do that, we do self.axis.text. So the axis object.text will return a text object, but also set a text object. And then in the middle, 0.5, 0.5. At the minute, we're going to give it nothing, so it's a text object with no text. It won't draw anything yet. We're going to give it a center alignment for both the vertical alignment and horizontal alignment. Color is an easy one because again, we can just get the color from the clock class. Color.colors, and it'll be the text color, so it'll share the same color as the text on the clock. Give it a transform of the trans-axis, so it should sit in the middle, irregardless of what the limits were, but I have set the limits to the same 0, 1, 0, 1 because I had a bit of a problem last episode figuring out how to transform this into a neutral expression that doesn't depend on limits, which is unfortunate, but time is precious, I guess. We can also give it a scale, so that should work. We do need a getUpdatables function again. So we need to tell the matplotlib object what changes, and all that changes on this one is the text object. So that's the text, and then we need an update function again, which we can copy over. So we'll copy the update function over, which is where we'll do stuff, so pass for now. We also need our increment function, and again, remember the increment function by default just increments, and we give it the optional ability to update with a DT. Sorry, update the plot. So in the update, what do we need to do? We basically need some expression that details, gives a decimal number based on the base. So that's quite easy. So self.text.setText. So this is how we set the text object. So we do a fast string. So we can put an expression in curly braces, curly parentheses, and we're going to want the integer part of self.time times self.frequency times self.base. So that's the product of all of those. And then we need to modulo that with the base. And then we'll format that so it always has two figures, I guess. Yeah, we'll format it so it has two figures, because when we have like a 12-hour clock, that's what we want. But for a binary clock, we don't want that. So let's have a separate speed hack for the binary clock. So if it's a binary clock, so if the base is equal to 2, self.text.setText, and then give it another fast string, and then curly parentheses for an expression. Then we want the int twice times the self.time times self.frequency, and then we need to AND that with 1. And then we do an else statement here, so if it's not a binary clock, do something else, which would be this expression. Let's just go ahead and see that works. We don't need to plot the entire thing yet if we don't think something's working. So let's call that num. Do you know what? I'm just going to call it a bit. Yeah, I'm just going to call it a bit, even though it's not necessarily a binary digit. Should have really come up with a better name for that. So yeah, base 12 scale. Scale. Let's do scale of. We really want this to be based on the figure as well. So I'm going to do scale equals 40 times the current figure size in inches, width divided by thing for now. Let's see how ridiculous this looks. And then in a plot update function, block.increment, we can do bit.increment by the same amount. It might end up massive. Yeah, text is way too big. Let's do 10 instead. Nope. I made the massive mistake of not adding it to the plot in the correct place. Call ax2, ax1 will live above ax2, that can be ax2, that can be x1. Plot that. What do we get? Well, that's not right. Really simple explanation is that I created another clock instance when it should have been a tmod num instance. Tmod num instance. Plot that. What do we get? Oh. Is that working? That's the question. And again, like most things in my videos, there's a very simple explanation for why it doesn't work, and that's because I didn't tell it that that's updated, and we're using blitzing on our plot, so we need to return a list in our function of everything that's been updated. So we need to say bit.getUpdatables, we'll splat that for good measure, go ahead and plot that. Something happened. So it appears that it's ticking every 12, so it's saying apparently we've got base 12, which is not true, because actually, even though our clock base 12, our seconds is base 60. Do that, and look what we get. We get a clock, so we've successfully managed to derive a clock. And it also shows something quite important, that the clock face, the actual numbers on the clock face is base 12, or base 12, but then with a decimal representation, so rather than going 9AB, for example, it goes 9, 10, 11. But the actual seconds itself is counting in a different base. Whereas the hours would be counting in the same base as the clock. So that leads us to getting into the meat of stuff. And now we're going to do something a bit different. So what we need now, let's do 12-hour clocks. So I'm going to create two variables, clock bases and display bases. So the clock will always show 0 to 12. So clock bases will be the actual numbers on the face of the clock. Display bases will be what we actually display, so the number at the top of the display. So display base here, which was base 60, and clock base, which is base 12. Okay, so a normal clock, the clock bases are all 12, but the display bases are 60. So seconds, you count 0 to 60. Minutes, 60 again, you count 0 to 60 minutes. Hours, you count 24. 0 to 24, or 0 to 23. So that's those two variables there. Let's go ahead and create something called digits. Digits will just be the length of the clock bases. So think of digits as more the number of clocks that we're going to display, because in binary that will be the number of bits, which is also the number of digits. F0 will be our lowest value frequency, so that's going to be 0.5, because we want the clock, in the binary clock, we want it to tick around 0, it needs to take 2 seconds to tick around, because it's bits times F0 gives you the frequency. DT, don't need DT. So the number of frames now, we can do something different. So T. Next, what we need to do is we need a value of T. So what is T? So T comes after F0, and T tells us the total time on our clock. So if you think about it, total time on a clock in seconds is 60 seconds times 60 minutes times 24 hours. So it's the cumulative product of all of those. And so that's what this function does here. So if I run that and then look at this value here. So T, 2880, is that correct? So if we look here, numpy.com product of display bases, that's 60 times 60 and then 60 times 60 times 24. Okay. We then need to divide by F0, because remember we're ticking at this rate F0, or this is how many times the first instance takes to tick around. So that will be our total time. So 2808 seconds. If we were ticking around F0. If it was a real clock, 1 divided by 60, let's look what T would be. 86,400, just doing the math. 60 times 60 times 24. Indeed, there are 86,400 seconds in a day. So that's good. Just realised you probably can't see anything I'm typing there. Yeah. So that's working. So this expression correctly gives us the total time required. And then we can do the total number of frames now is a bit more intelligent, because we know this clock here would be ticking for 86,400 seconds. At 60 FPS, we know that it's the product of those two, to which the total number of frames of our animation would be. Going to be a bit more intelligent as well, because remember here we had the fixed size was a fixed figure size. What happens if as we add more of these clocks, we actually want it to adjust slightly. So we'll give it a constant width of say 15 inches. and then we adjust the figure height in order to be this expression here. So we create the plot, that's fine. And now we want to actually do this a bit more clever. So add clocks and bits based on these two values here. So clock base and display bases. So we can get rid of all this. Let's create three variables: clocks, we're calling them bits, but they're not necessarily bits, and updatable. So we might as well keep track of things that we're going to update now, so we don't have to call it every time inside the plot function. And then all we need to do is for base and display base in, and then we go ahead and zip the clock bases and display bases. So clock bases, display bases, they get zipped together. So that means in this function here we have access to clock base and display base, and they come in the right pairs. So the way these are done here is that the display bases go in ascending order, and so do the clock bases. And then what we'll do is we'll put them in the plot in descending order, so from right to left instead of left to right. One more thing we do need to do, in order for us to do that, we need to know what current number we are in terms of clock base and display bases. And that's easy because we can add a I comma to the front, and then we can just enumerate our zip, which will return a tuple of whatever was in the enumeration and I. So I and then whatever was in the enumeration, which again itself was a tuple, which is no problem because Python can quite happily unpack tuples all day long. And now we need to think, what we said at the beginning of the video was that the clocks are basically independent. So they don't need to know anything about any other clock, and that's what makes this so nice, is that each clock, just as long as it has the right frequency and the right phase, so as long as they all start off in the same place, which you've manually input here, so they all start off at the top, then all we need to do is give it the right frequency. F0, which was our base frequency, and then we just need to make sure that we can scale it by the required scale factor. So we know here that F0, or the first clock, should be F0, okay? For the next clock it should be 1/60th of that, and for the next clock it should be 1/60th times 1/24th of that. So in each case, the cumulative product of this scaled to the first value here. What does that look like? Well, that is numpy, umprod, cumulative product. We need to do the display bases, but remember the first display base was 60, we want it to be scaled to 1, which is quite easy. We just divide by the first display base. And then we need to pick out the correct value of that. So we pick out the correct value, which is I, because we're enumerating through. So the first frequency is simply going to be F0, the next frequency is going to be F0 divided by 60, the next frequency is going to be F0 divided by 60 divided by 24. So that frequency is now correct. And that's really simple now. All we've done is say we've got the correct frequency. It's now literally just a bit of code to create these bits and these clocks. So bits.append, remember we're going to append all these bits, so keep track of them. I'm going to create a tmod number class, so tmod num. And again, we know that requires a frequency, which we've just calculated. Requires an axis. So this one, we do fig.add subplot. I'm doing this all in line at the minute, just so it's a bit easier to keep track of. Well, so it's a bit more compact. Remember we created this grid, so grid spec. It needs to go 0, so the numbers go at the top, so row 0. But then its position needs to go from right to left, not left to right. So we can't just count I. We need to count from digits, which remember that in this case would be 3. So we need to do 3 minus 1. And then minus 1 again, because remember indexes go from 0, start from 0. But this digits here is 3. 3 minus 0 would be 3 still, so you need to minus additional 1. Base, and then literally, again, because we've zipped together the clock base and display bases, we know that this is the current display base. And again, we're using display bases and clock bases because the clock might not look like the display, which is the case for a normal clock. And then let's go ahead for the scale and say, let's give it 40 times the current figure width divided by the number of digits. So hopefully this should be quite scalable. So as we start adding different amounts of clocks, in particular the binary clocks, as we add different amounts of bits, this should hopefully scale nicely so that as we keep adding them, the text size shrinks accordingly. Okay, and then we do the same for the clocks. So clocks.append, remember clocks and bits are just these lists to keep track of them. So go ahead and add a new clock object. And again, do you know what? This is almost the same, so we'll copy this over. So it gets a frequency, gets an axis, but this time the axis on the bottom row instead of the top row. Still gets the same display base. No, it doesn't. It gets the clock base now, because it was talking about the actual clock, not the number at the top. And for the scale needs to be something a bit different. 22. I don't think this needs scaling with the plot size at the minute. because that does scale based on the number of numbers, but we can come back again and scale that. Because at the minute I can't quite see why that's not scaled, but we'll come back and scale that. It seems to have just worked before. Look at this. This happens sometimes. So sometimes when I save the file, I end up getting like weird glyphs. So look, it's actually imported a smiley. I don't know how I do it. This happens more often than not. So strange. So strange. And then all we need to do now is make sure we have our updatables. So remember, updatables just a list of things that have changed. That's really easy. We can literally just say the last bit that was added, just get the updatables to it and add it to this list of updatables. So in our actual update function, we can just say splat the updatables. So here's a list of everything that's changed, which are the only things that change in each clock and tmodnum class. And then this is a nice little hack. So as long as if the frame's not equal to 0, we'll go ahead and actually do some stuff, because when we call this increment function, it increments dt and then updates. So there's going to be a problem is that during the first frame, it's going to update. It's going to increment dt first and then update. So we're not going to get our default position where all the clocks are facing upwards during our first frame if we don't do that. Because the way we've implemented it here is increments dt and then updates, which is the behavior you would want. But for the plot, that's not the behavior we want, so we need to just guard against that. But this update will still work. These updatables are still updated because during the initialization, all this was created, in which actually we should put that here. Yeah, in the initialization for each of the class self update, just to make sure that it actually puts the right text on, because for example, this tmodNumber class, we said don't plot any text at first, so we need to do update in order for it to actually update the initial value. So actually basically so it shows a 0 when we start, or the correct 2 zeros when we start. Likewise, we'll do that here, self.update. So if the frame is not equal to 0, we can go ahead and do some updating. And then it's really simple. We just do for, again, we can use our zip function, but the bit in the clock, in the bits and clock, oh dear, always check your capital. Clock in zip bits and clocks. And then we just need to do bit.increment dt, and remembering that update equals true because we want it to update, and clock.increment dt update equals true. Hopefully this should work. dt is not defined. Well, that's silly because dt is really easy to define, because dt is just going to be 1 over the fps. Return splat the updatables. And the reason that's not worked is because in our figure we didn't tell it the correct number, sorry, in our grid spec we didn't tell it the correct number of rows and columns anymore. Because remember, now we need to adjust the number of rows, which is quite easy because the number of rows is now simply, sorry, the number of columns is now simply the number of digits. tmodNumber no attribute.getUpdatables, and that's because I've changed the name. So I had camel case, save that, give it a nice little format. tmodNumber no attribute.getUpdatable. Updatables. Always check your spellings. Annoyingly, it keeps opening on the other screen. We can see that looks to me like it's working. So that's exactly what we wanted from the beginning of the video. We have a clock on the far right. That's simply ticking around once every 60th, well, once every minute, or more precisely, it's ticking around at a frequency of, it's actually not right on this one. It is actually working, but it's the FPS can't keep up. So the FPS is not going at 6 frames a second, so it's actually slowed down. So if I've changed now the FPS to 1, it actually looks really good because now it literally ticks every second. We can actually count it now, it's actually ticking at the correct rate. Good, so we created a normal clock. This one's going around once a minute, this one will go around once an hour, this one will go around once a day, with the numbers at the top going from 0 to 59, 0 to 59, and 0 to 24, 0 to 23. Exactly what we want. And now because we've done it this, well, I say object oriented. This at the top is object oriented. This at the bottom is actually functional programming. So it's a bit of a mixture of the two. A really easy way to cheat that, you just put all this inside of a class, create one method called run, and then just call that objects.run. So you can fudge that quite easily. But for now, it's just a mixture of object oriented and functional programming. And let's just go back and have a look. So it should be quite easy to create a binary clock. So let's take the clock bases off. Let's create a new one. So clock bases, remember this is what the clock shows, so that's going to be 2. Let's do 6 bits. Let's do display bases, and that's going to just be the same clock bases. We're going to go from 0 to 1. Okay, and because it's binary, we don't want to count 1 over 2, which is the 1 over basically the base. Let's play that. Seems to be working. Probably increase the FPS on this one. There's no reason why. Oh! And there we go. Something very nice has happened there. Go ahead and increase the figure size back to 15 inches and we should get a nice scaled plot. And that is exactly what we set out to do. So we've used object-oriented programming in Python. We've used some knowledge about clocks and how actual clocks tick along to actually implement a binary counter. So every second the bit tier changes from 0 to 1, 0 to 1, 0 to 1, etc. And we can also see how in certain circumstances, when all these values are 1, they will all line up here on the 0 mark and then increment the next bit. So we'll see it again. Let's keep watching. These 3 bits are about to line up. Here we go. All of the clocks line up. Boom, changes. And now we have to watch this clock. Watch them all line up as it shifts the bits along. So it's a different way of thinking about counting as well. It's basically when all these clocks synchronize, boom, it'll move the binary along. And I think that's quite nice to actually be able to see. And I had another one that I did. So while trying to do this video, I was doing some other things and I ended up creating this animation, and I actually think this animation looks really nice. I think it perhaps shows a new way of looking at counting in binary. So the way this does now, it only ticks whenever there's a 0. Whenever it's 1, it will spin round. If it's 0, it's stationary. But you can sort of now see how the sort of 1s pass along. So when the red spins round, it basically picks up a 1, and then it spins round, and then it gives the 1 to the corresponding next bit. But if they all line up red, then that sort of 1 shoots along. It's just a really strange way of looking at it, but I think it also showed something quite nice. I think maybe in a future video we can maybe program this in. It's going to be basically the same. In this particular case I did functional programming, so there's no object-oriented programming here really. I say that Python is a mixture. A lot of the time when you're doing functional programming you're constantly just calling some objects, like all these figx objects for the figures, they're all object-orientated programming. But it'd be quite interesting to see this, and it wouldn't actually be too much difficult to adapt what we've already done in terms of the object-oriented base programming for the actual previous clocks and actually adjust this, because it's basically just saying offset the arrow to the left instead, don't bother drawing a clock, and only move for half of the frequency, basically only move a half of the time period per frequency. We'll just go back to our binary clocks, which again I think are quite nice. And just for proof of principle, let's change that to 8-bit. We should see it keeps the same width for the figure, but then the height and text is adjusted accordingly so that we still get a really nice looking plot, really nice looking animation. And again, so this is now an 8-bit counter. So this is counting a frequency of 2 Hz. So it goes through, think about binary, it's 2 bits, right? Binary is 2 values. So this needs to tick at a frequency of 0.5 Hz in order for each state change to be 1 Hz. So it's 1 Hz divided by 2. So that's how the counting in binary is done. And so look, 1 Hz, half a Hertz, quarter of a Hertz, eighth of a Hertz, 16th, 32th, 64th, etc, etc of a Hertz. So yeah, I hope some people watching this have found this interesting. And again, it's one of these things where it might be you don't quite understand how binary works, or you maybe know how to count in binary, but there's no other way of thinking about it in your head, like thinking, oh yeah, imagine it's just a clock where each bit is just ticking at half the previous frequency. I think this is actually quite a nice way of actually showing how you can think about binary counting. And I'm all one for doing these things where you present the same data in a different way, try and make it more memorable. And I'm always finding that actually seeing an animation of something is by far the best way of remembering something. That was a nice one. So yeah, I'm a massive fan of doing things like this, and I'll keep doing things like this as long as people are interested. So I mean, leave a like if you found this interesting, because it always helps me to know whether these are the sort of videos I should be doing or whether I should be focusing on some of my other videos, etc. But I think this has been a really nice video, so thank you for watching if you've managed to watch both parts, and I'll see you in another video.